So, we are discussing the DC link control. There are 4 control variables: the delay angle alpha for the rectifier alpha r, the extinction angle gamma for the inverter gamma I. So, for normal operation gamma I is also the commutation margin angle. Then the on-load taps that are present on the transformer on the rectifier side as well as the inverter side, TR and TI. So, what we try to do is we try to regulate one of the quantities using these control variables. So, we do what is known as constant extinction angle control. Constant extinction angle CEA control of inverter by regulating gamma I. So, gamma I is kept constant so that it does not go below that value. Okay. So, the intention is to see that we have a minimum commutation margin angle for the inverter. See, for the rectifier the commutation is not an issue. Okay. Then we use the constant current control, what is known as we try to regulate current. So, in the last class we saw that there can be fluctuations of the current, so which can damage the weak component, that is the valves. Okay. So, what we do here is employ constant current control, which is abbreviated as CC control. Is employed at regulator, employed at rectifier, is employed at rectifier. Now, when I say constant current, we are trying to regulate some current. That current is the DC side current to regulate ID. So, what is used here? Alpha R. Okay. So, this is using alpha R. So, that means we change alpha R in order to control ID to the required value. Okay. So, if for some external disturbances ID changes, okay, if ID tries to change, we change alpha R in order to bring back ID to the desired value. Then we also use the 2 slow controls TR and TP. So, TR is the on-load tap ratio, actually off nominal tap ratio at the rectifier side. Say off nominal tap ratio means something which has a nominal value 1, TR nominally is 1. Okay. So, in practice it is close to 1, greater than 1 or less than 1. So, on-load tap changer at rectifier so this is TR is used to maintain alpha R. See, alpha R is maintained within certain limits. So, though we say that having alpha R close to 0 or 0 in fact will have some advantages of improving the power factor, reducing the dV by dt stress, but we want to maintain some margin for control whenever there is low voltage on the AC system. So, if there is a low voltage in the AC system, then we can use alpha R to see that the DC voltage is regulated. Okay. So, that is why we maintain alpha R not at 0, but within certain limits, close to 0 of course, within certain limits. So, this limits, for example, say 15 degrees to 20 degrees. So, this is done in order to leave some margin for increasing the voltage. So, leave some room for increasing the voltage. when, so when this necessity comes for increasing the voltage, when the AC system voltage for some reason comes down. Actually say during overload condition, suddenly a large load is there on the AC system, say on the rectifier side, then the AC voltage comes down, means the DC voltage will also come down. But by using this margin for alpha R, we can actually increase the voltage. So increasing the voltage when there is a drop in the AC system voltage. There is one more control variable, that is Ti. So now how do you use Ti? How do you use Ti? See, there is an on-load tap changer at inverter. See, all of these are used to regulate one particular quantity to a desired value or within a certain range. Say for example, this TR is used to maintain alpha R within a certain range. Similarly, constant current control means there is no range, the range is of 0 width. ID is ID is regulated at a certain value. Say, when you talk about control, most of the times we are talking about the type of control that we come across in power systems is either maintaining some quantity at a particular value, at a desired value, or maintaining it within a desired band. That's all we want. We don't need any other type of control. Okay, so if I want to maintain ID at a certain value, it's as good as saying that the band is of 0 width. In the as far as alpha R is concerned, it is not of 0 width. No, it's a non-zero width. Say I've given an example, 15 degrees to 20 degrees. Similarly, constant extinction angle means 0 width. We are maintaining the extinction angle at a particular value. Okay. Now the on-load tap changer at inverter, that means the variable is Ti, is used for what? Is used to maintain the DC side voltage constant. Is used to maintain constant DC voltage. So this is how the 4 control variables are used. Now let me just redraw the circuit that is applicable for the DC link. So we derived this circuit. See, this is just an equivalent circuit which represents the equations governing the system. So I have the voltage EDR here, EDI, RCR, minus RCI, RD. RD is the physical resistance of the transmission line, and the voltages which are actually present in a physical system are VDR and VDA, and ID is also a physical current that flows in the DC transmission line. But RCR, RCI, EDR, EDI are just representations. Now, if I look at this circuit, if I look at the inverter terminal voltage, the DC side voltage, VDI, this can be written as EDI minus RCI into ID. Similarly, I can also write VDI in terms of EDR, RCR and RD. So VDI is also equal to EDR minus RCR plus RD into ID. Right? Now let me try to take the graph of VDI as a function of ID. Okay, let me draw this. VDI as a function of ID. So, should I consider all the 4 quadrants is the first question. Should I consider all 4 quadrants? Is operation, say I just take VDI and ID, is operation possible in all the 4 quadrants? Yeah, then what? VDI is always positive. ID? See, the point is, once I decide one converter as rectifier and one converter as inverter, okay, then say if you go back earlier, we consider this graph VDID, if you recall, okay. ID is always positive, so that means operation is possible in the first and fourth quadrant, because VD can be positive or negative depending on the converter acts as a rectifier or inverter, whereas this second quadrant and third quadrants were not allowed. Now, first and fourth are allowed because it's the same converter can operate both as rectifier and inverter. Now, I have 2 converters now in the system, one is fixed to be rectifier, another is fixed to be inverter, so there is no change of role. Okay. So, if that is the case, then the same converter operating as both rectifier and inverter is ruled out. So, that means either I have first converter operation, quadrant operation, or second quadrant operation. Okay. So, I have actually put the positive and negative sign in such a way that VDI is positive, so always positive. So, only first quadrant is allowed. Okay. So, let me erase this. So, only first quadrant is allowed. Okay. Now, if I take one of the controls, see, one of the controls is constant current control. So, for constant current control, what will be the characteristic, steady state characteristic? Let us look at only the steady state characteristic. We are not worried about the transients. So, in this course, we will not look at the transients that are involved. So, suppose I employ some controller to regulate the DC side current, that is constant current control. See, just now I mentioned constant current control is employed at the rectifier side to regulate ID, which is done using alpha. So, what will be the characteristics in steady state in this graph? Straight line. What is the slope?
Negative slope and
Positive intersection, negative slope. Will that give constant current? What is current? What is this current? This current is ID. So, ID is constant means vertical line, that is all. I have just a vertical line. So, I have some vertical line here. Okay. What I will do is I will try to use a different. So, it is just a vertical line. So, this is CC control. This is CC control. To be more precise, I employ CC control at rectifier, for rectifier. Okay. Now, what do we do at the inverter? What type of control do we employ? Say, if I just look at the fast control, that is the control of alpha R and gamma I. So, gamma I is actually constant extinction angle. So, gamma I is constant. So, if gamma I is constant, then what will be the steady state characteristics in this graph? See, in this graph, VDI is plotted as a function of ID. So, what will be the constant extinction angle characteristic in steady state? Okay, what is yes, straight line, slope, what is the slope? Minus RCA, okay. What is the, I mean, where does it intersect the VDI axis? Yeah, so just look at this equation. VDI is equal to EDI minus RCI ID. Now, is RCI constant? RCI is constant for a given tap. Okay. Now, what about EDI? Yeah, we are fixing gamma. It depends on gamma. See, if all other things are constant, look at the expression for EDI. So, I mean, I presume you all have the expression for EDI. What is EDI? EDI is, if you recall, we got the expression for EDI as 3 root 2 by pi into NB. 3 root 2 by pi, NB is a constant, number of bridges. EVI. So, EVI is the RMS value of the bus on the AC side of the inverter into cos gamma I. So, if EVI is assumed to be constant, then by constant extinction angle, gamma I is constant. So, EDI is a constant. So, if EDI is a constant, then the plot of EDI as a function of ID is a straight line with a negative slope. So, if I plot so, this has a negative slope and it intersects the VDI axis at EDI. So, this is CEA control for inverter. So, that means the point of operation is the intersection of these two characteristics. So, these two are steady state characteristics. So, at this point P, the system operates. So, the value of VDI and ID are obtained from the intersection of these two straight lines. Is that clear? So, we employ CA control for inverter and CC control for rectifier, means these two controllers will give to two characteristics in steady state, which are both straight lines. One is a vertical line, other one is a line with a negative slope. So, the intersection of these 2 points is the point of intersection, which gives the point of operation. So, the value of VDI and ID are obtained as the values at this point of intersection of these two straight lines. Okay. Now, there are some problems. I mean, say as long as everything is normal, it is okay. But sometimes what happens is, if I try to again take the same graph, VDI as a function of ID. Now, if I take this constant current, the least value of VDI along this red line is 0. Now, what is the highest value? Can it go infinitely? Yeah. What is the maximum possible value of VDI along this straight line? No, where does it stop? No, suppose I just consider only the CC control characteristic for rectifier. I will come to the inverter later. So, can I say, I am just taking one curve at a time now. So, earlier I said these are all infinite straight lines, at least on one side. So, the other restriction is that it is lying in the restricted to the first quadrant, but I have not shown the other end of the straight line where it will stop. Say at least this vertical line, it appears as if, say the other one has a negative slope, it may at some point actually intersect the ID axis, and then we can say it stops there. But as far as CC control is concerned, when I say it should lie in first quadrant, it appears as if the other point is at infinity. But in practice, what decides the other end of this vertical line? Yeah, suppose the supply voltage is constant, the AC side voltage is constant for the time being, and we just consider the fast controls. Okay, so forget about the slow controls, assume them to be constants, and even the other voltages to be constant. The AC side voltages are constant, tap ratios are constant, the off nominal tap ratios. Then how do we get the other end? Is there a limit first of all for the value of VDI along this line? Yeah, what is that? How do we get that limit? Alpha is equal to 0. Yeah, say as you go up and up along this, okay, as you move vertically upwards, alpha R actually is decreasing. See, constant alpha characteristics we know, right, for a converter, they are all straight lines with negative slope. So as you keep on increasing alpha, you get the straight lines which are below the values which are for lower value of alpha. So that means as you move along this line, alpha R is actually decreasing. Alpha has a lower limit to ensure adequate voltage across the valve to turn on. Now the question is, if alpha is fixed at the minimum value, what is the variation of VDI as a function of ID? See, I think you have forgotten this constant. See, there are three types of characteristics that we studied, right? Constant alpha characteristic, constant gamma characteristic, constant U characteristic. There are only three types of characteristics that we studied. Now, in this case, we should not even bother about U greater than 60, that is abnormal operation. We are looking at only normal operation, U is less than 60. So, we already studied all these types of characteristics. So, we know how the curves of VD as a function of ID will be for all these things, you know. So, if I say minimum alpha, it is constant alpha. Minimum alpha means constant alpha. So, constant alpha, what is the characteristic? Straight line with a negative slope. So, it is a straight line with a negative slope. What is the slope? Minus? No, you are talking about per unit, is it? You are talking about per unit. Here I have not actually normalized. I am taking the quantities as it is. Yes? RCR plus RD. Look at this equation. See, go back to this equation. Okay, it is RCR plus RD. Now, first of all, is EDR constant? What is EDR? So, EDR is 3 root 2, yeah, instead of gamma we will have alpha R, that is all. So, 3 root 2 by pi NB EVR cos alpha R. So, when I say alpha is minimum, that means it is a constant. So, if alpha R is constant at the minimum value, then EDR is a constant provided EVR is constant. So, we will assume that EVR is constant. So, EDR is a constant. So, if EDR is constant, then the variation of VDI with respect to ID follows a straight line. But what will be the slope? The slope is RCR plus RD. So, is the slope greater than the CA characteristic slope or less than that? See, the previous CA characteristic, what was the slope? Okay, let me go back to this curve. What is the slope of this? Slope is minus RCI. Now, for this case, in the case of minimum alpha R, the slope is equal to minus RCR minus RD. Okay. If I just look at the magnitude of the slope, which one is larger? Now, please note RCR and RCI are almost same. The only difference is because of taps, that is all. Because of taps, the leakage reactance depends on the tap position. So, that is a very small variation. So, due to tap changer, we have different values of RCR and RCI, but they are close. So, RD is much larger than the difference between RCR and RCI. So, that is why the slope of the minimum alpha R characteristics is larger in magnitude compared to the slope of the CEA characteristic for the inverter. See, what I am trying to say is RCR plus RD is greater than RCI, because RCR and RCI are close. and RD is much larger than the difference between these two. Okay. Now, what is the implication? See, if just look at these two graphs. So, in the first graph, point P was the point of intersection of CA characteristic or CA control characteristic of our inverter and CC control characteristic for rectifier. Okay. Now, due to reduction in the rectifier side AC side, rectifier AC side voltage, then what can happen is alpha can keep on decreasing, but at some point it can, okay, what I will do is I will try to draw a graph where both CA characteristic is there and minimum alpha R characteristic is there. Okay. So, let me draw one more graph. So, I have VDI, I have ID, I have minimum alpha R, okay. Now, there is a CEA control also. So, CEA control has a slope which is less than the minimum alpha R control. Okay. So, please note I will be using some fixed colors for the controls. Red means CC control for rectifier, blue means CA control for inverter, green means minimum alpha. I have marked all these things, red for CC control, blue for CA control and green is minimum alpha. Now, if P is the point of operation, now suppose the AC system voltage on the rectifier side actually decreases. Now, what happens to minimum alpha R? See, alpha R is constant, but the AC system voltage on the rectifier side decreases. What happens?
Goes down.
So, the curve actually moves. Alpha R is constant. The AC system voltage decreases. The DC voltage also decreases. VDI is DC voltage. So, alpha R is constant. Okay. So, this minimum alpha R also decreases. Now, it can go to a situation where the minimum alpha R can go down like this. Now, if minimum alpha R goes down like this, what is the point of, at what point the system is operating? Say earlier with this minimum alpha R, the first minimum alpha R, the point of operation was P. It was, this first minimum alpha R is not even deciding the point of operation. The point of operation is decided by the CC control of rectifier and CA control of inverter. Now, when it comes to a situation where I have a reduced voltage on the AC system of the rectifier side, then the minimum alpha R is actually gone down. Now, what is the point of operation of the system? Intersection of course, obviously it is intersection of two line segments. Which are those two? Okay, let me, red and green. See, okay, what is this green? This green is for the, see, when you say red and green, the point of intersection of red and green, CA is not maintained, CA is avoided. See, if I want to maintain constant extinction angle, I have to be on the blue line. Constant extinction angle means I have to be on the blue line, that I can't violate. So, intersection of the new green curve 2 and red line means I am moving away from the blue line, which is constant extinction angle. It should be green and blue. The green is the new control at the rectifier now, and blue is of course the still existing constant extinction angle at the inverter. So, the new control is this. So, new control is the second green line, and the point of intersection of the second green and blue gives the point of operation. Now, this is also slightly okay, but the problem is now the current is no longer regulated, current is not regulated. Okay. So, say either you have to avoid regulating current or avoid regulating constant extinction angle, but what we normally do is we maintain constant extinction angle. Suppose this happens. Now, if this condition worsens, that means the voltage goes further down, then the minimum alpha R characteristic will be even below. Suppose it goes to a situation where this blue and green also does not intersect. Okay. So, this is 2. Suppose this is 3, then there is no intersection. Now, what is happening? Say from 1 to 2, if I look at the original condition P, and then the new case is operating at say Q. Okay. From P to Q itself, there is a reduction in the current. Now, when the condition worsens to 3, then ID would have become 0. ID can't be negative, ID is 0. Okay. So, even before this green curve 3, there is a slightly a curve which is slightly above, which intersects the blue curve just on the VDI axis. At that point itself, ID would have become 0. So, when ID becomes 0, we say that there is a rundown of the DC link. So, when I say ID equal to 0 means the term used is rundown of the DC link. Okay. Now, this has to be avoided. Say rundown of the DC link means no power transfer, ID is 0 means no power transfer. So, to avoid this, what we do is we provide what is known as constant current control even at the inverter. So, let me try to redraw. VDI as a function of ID. So, I have shown one red line constant current control at rectifier, one green line minimum alpha R, that is also at rectifier, then CEA control. So, CEA control is the blue line for the inverter. Now, what we normally do is if the situation of rundown can occur, then to avoid that we provide a constant current control even at the rectifier, even at the inverter. So, then so please note the red one is CC at rectifier, CC control at rectifier. Then the blue one is actually CEA control at inverter. Then the green one is actually minimum alpha R obviously at rectifier, because alpha R means alpha, the subscript R stands for rectifier. Now there is one more purple. So this one is actually CC control at inverter. Now what happens? Say we see that there are 4 line segments. There are 4 line segments. Okay. So 1, 2, 3, 4. Now among these 4, 1 and 3 are for rectifier, whereas 2 and 4 are for inverter. Okay. Now when the system is operating normally, then the intersection is actually that of the blue line and the red line, that gives the point of operation. Now there can be a problem of reduced voltage on the AC system of the rectifier side, then the green curve can actually shift down. So the shifted green curve, I will just show it as a dashed curve. Okay. So this so I have shown as if the intersection of the new green and blue is possible. Now you see that the current has reduced, ID has reduced. So yeah, earlier the point of operation was the intersection of blue and red. Now it is a new green and blue. Okay. Now if there is a further deterioration, then the green one will not intersect the blue curve, it will intersect the purple curve. Okay. So I have shown 3 points. Okay. Let me try to exaggerate this figure. It's slightly unclear. Okay. I am just trying to exaggerate. So that there is clarity in the figure. Okay. So the earlier point was P, the revised point is Q. If there is further deterioration in the DC in the AC side voltage of the rectifier, then the point of operation is this R. So if you look at the point of operation, originally it was the CC characteristic of rectifier and the CA characteristic of inverter, that is normal operation. Of course, due to some reason the voltage on the rectifier side comes down, then it is no longer the CC characteristic of rectifier coming into picture here. So if you look at the green, the revised green and blue intersection, CC is not playing a role here. So it is a minimum alpha R characteristic of rectifier and the CEA characteristic of the inverter. Then if there is further reduction in the voltage, the green curve is further reduced, further going down, then R is the point of operation, which is the point of intersection of minimum alpha R and constant current of inverter. Okay. So if you employ this additional constant current control at the inverter, then we see that the current ID will not become 0. Okay. So if you compare this with the previous graph, that purple curve was not here. So the purple curve is additionally introduced. So in the previous case there was no purple curve. So without the purple curve, ID will become 0, there is rundown of the DC link. So we employ this current control, constant current control at the inverter also, so that the current will not go to 0. Okay. So there is a small difference between the constant current employed at the rectifier and the constant current employed at the inverter. The current which is desired, the desired value of current at the inverter is less than the desired value of current at the rectifier. So the difference is called current margin. So this current margin is typically 10% of rated current.